concept that I want to mention here is, let's say, there are some confusions when you're starting out, that when to use map and when to use structs and all. So maps and structs have a lot of differences. For example, you cannot do this with a struct. You cannot loop over all the fields of a struct because struct is a static type in Go. You already know all the fields and all the values of a struct somewhere. It is already written. You don't have to loop over it. That is the first difference, that you cannot range over structs, but you cannot range over, but you can range over maps. Second, all the values inside a map, like this is not a variable. This does not have a fixed memory location. You cannot use this to initialize a pointer because this does not have a memory location. On the other hand, every struct field has a fixed memory location and you can use that everywhere. And that memory location will be fixed because map internally uses hashes and buckets and a lot of internal algorithms to hash and to do lookups and to add keys, remove keys and all. So they don't have fixed memory locations. The memory locations keeps changing as we add more keys and memory values. That's the reason the memory location of maps are not fixed. The third thing is also this part. When we are iterating over maps, the order in which we get the keys are not fixed. They are intentionally randomized so that you don't depend on the order to be the same. If you want the order to be the same, you have to explicitly sort the keys yourself. That's also something to remember about maps. And coming back to this, another difference between map and struct is just the use case, that we use structs to store data. That is a very oversimplified definition that I have come up, but this is the idea on a very high level. And we use maps to look up. That's a mental model you can use whenever you want to differentiate between maps and structs. So let's go and take a look at what some real world maps look like, how people use them. Then here you can see there are a lot of use cases of maps. People are using it all for parsing random JSONs into structs and mapping HTTP headers there, because HTTP headers can be of any type, right? There can be a lot of different types of headers and you don't know all the types. So in those scenarios, you cannot use a struct. You have to go with a map because you want to assign any string and for the key and any string for the value. This is one perfect use case for maps that we typically use for. And there are others for whenever you want to parse any kind of JSON into a Go data type, then you can go with map. If you don't explicitly know the keys and values of that JSON, in that case, you can unmarshal it into a Go map. Then you can access it. Okay. So there are a lot of different use cases for maps. Another concept after that I want to cover is, in Go, functions are first-class citizens. And by that, I mean there can be anonymous functions also. So here we have a function declaration which does not follow the typical function declaration that we have here. Here we have the func keyword, then we have the name of the function, then the curly braces start. We don't have the same structure here. What you're doing, since functions are first-class citizens, you can assign a function to a variable right inside any function. So what we are doing here, we have a variable, we are using the short declaration form, and we are assigning a function to that. What this function does, it takes two parameters, x and y, which are of type float64. It returns the same type, float64, and it actually does this math calculation. It does x into x plus y into y, and it calculates the square root of that and returns it. This is what this function does, and we are assigning this function to this variable. Now we can use this variable's name to perform the calculation. We can use this variable as this function. And as you can see here, we are calling this with two arguments, 5 and 12, and this will be x, this will be y. Okay. So this is one of the features of functions being first-class citizens. You can assign functions, you can assign anonymous functions to variables. Now the second thing, we have a function here. We have a function here which takes another function as a parameter. We can also do that because functions are first class citizens in Go. We are taking a function as input, and what this function's signature is, it takes 2 float 64 and returns 1 float 64. And if you see, this signature matches this signature. We don't have to write the name of the variables here because this is just a signature of the function. Okay, and this is used as a parameter of another function, and in this case we don't have to write the variable names. Okay, it takes another function as a parameter and returns a float 64 value. And in the function execution, what it does, it uses this function to do some calculation with 3 and 4, and it returns the value. Okay, and because of that, because it takes any function and it passes 3 and 4 inside that, that's why now we can use any function whose signature matches this. So for now, we have this function whose signature matches this. We can pass the hypot, this function, into this function compute, and we will get the result. The same way, we have an inbuilt function which is math.power, which has the similar signature. As you can see, math.power, we has x float 64, y float 64, and it returns a float 64. Since the signature matches, we can also pass this function inside this. And if you try to run this, we will get expected results. We have a print statement for this line, then we have this line, and then we have this line. And this everything works in a very smooth manner. And this is a very nice feature of Go. And we can do a lot of composition by passing functions inside other functions and a lot of other advanced features. Because we can pass functions into other functions, Go provides another nice feature called closures. Now, if you are a JavaScript developer, you are coming from a JavaScript background, or any other programming language which has the same feature of closure, which I'm not aware of, I'm aware of JavaScript, then you'll get it. It works exactly the same as other languages, the same as JavaScript, the same way closure works in JavaScript. But if you are a beginner and Go is your first programming language, or you are coming from a programming language which does not have the concept closure, then I would say don't take it too seriously. Don't try to understand everything around it. Just know that this nice feature exists and they are used in a lot of places, in a lot of libraries. You might not use it explicitly, that you won't think like, now I'll use closure for this. But closures are used implicitly in a lot of places. So just know the concept that it's there, and it's not a big deal if you don't understand it right away. Now, this is how it works. This is how closures work. We have a function, and this function returns another function. And this function has access to the variable of the outer function. It has access to sum. Now, because of that, even after this function returns, it has access to a state called sum, which it can keep using. And let's use this example to understand how exactly this works. So let's first run this. Okay. We have different iterations. Let's go through the iterations first. Now, first, we are initializing two variables by calling these two functions. The result of this will be assigned to this. The result of this will be assigned to this. Okay. And the positive, and both of these are different functions of this instance, this type, which takes an integer and it does this calculation with sum and it returns the sum. Now what happens in each iteration? We come inside, now I equals to 0, and we call this function, the positive function, with I. Since I equals to 0, sum equals to 0, sum plus I, which is 0. So here we see 0. And in the same way, in the negative call, we are multiplying I with -2. And we know multiplying anything with 0 is 0. That's why we are also getting 0 here. In the next iteration, now here I's value is 1. Before that, I's value was 0. That's why I got 0, 0. Now I's value is 1. What happens now? It comes inside, it calls this function positive of I. And then we go here, x is 1. Now sum plus 1. Now since sum is 0, sum plus 1 is 1 and return sum. So now this is 1 for this part. Now for the negative part, we minus 2 into 1 is minus 2 and minus 2 is here. Minus 2 plus 0 is minus 2 and then we see minus 2 here. Okay, that is this iteration. Now in the next iteration, i's value is 2. We come here, we call positive with the value 2. Now what is the value of sum? Now the surprising part is sum's value does not start with 0 here. Sum actually remembers the previous call, and because this positive is the same instance of calling this function, it will remember the state of sum across different function calls. That is what closure means. Closure basically means if we have a scenario like this where an outer function returns an inner function, then that inner function will have access to the outer function's variables even after the outer function returns. Okay, and because of that, the inner function can use this as a state across different function calls. That's the reason in the next iteration, when i's value is 2 and we pass 2 inside positive call, now in the previous iterations, sum's value was 1 and it remembers that. That's why 1 plus 2 is 3 and we see 3 being printed here. That's what closure basically means. It's not a concept that you will explicitly use everywhere, but it's still an important concept and it's used in a lot of places, and it's good to have the knowledge that how it works or it exists basically. Now Go provides a feature called methods, which allows us to assign functions to types, any type. It can be struct, it can be integer, it can be string, any type, any custom type, as long as that type is defined in the same package. That is the condition that we have to match to assign methods to a type. Now we'll typically see types being assigned to structs, but there are also use cases of types being assigned to user defined types, like custom types that take from integer or strings and arrays and all. Okay. Now, how does it work? How do methods work? Let's first look at the syntax. We have a struct here, which is, and whose name is vertex. It has two fields, both of type float64. Now, in the next line, we are defining a method on the type struct. What it does is, this part is the same as a function declaration. Okay. If we had a function called abs, then this is what it would look like. It would have a name, it would have a braces, and then have a return type and the execution statements. This is the typical function declaration. But a method is different from a function in a way that before the name of the function, we have the receiver. This part is called the receiver. And this type, and whichever type this matches, then we will say that we are defining a method called abs on the type vertex, because in the receiver we have the type vertex. That's how we assign a method to a type. That's about the syntax. And then we have here available v, which is of type vertex, which is a struct. And this is an instance of the struct, not the type itself, but a concrete instance of the struct. And usually we write a short variable because we'll again and again have to access that, but you can make it readable also. It is not that important. And using this, we will have access to the fields of the structs here. We have access to the fields of the struct, whichever struct we are calling this method on. Now, in order to see the use of this here, we are declaring a variable v, and please don't confuse this with, this is a parameter, this is a variable declaration in another function scope. Now we are declaring a variable which is of type struct, a struct called vertex, and we are assigning 3 to x, and we are assigning 4 to y. Now v is a struct, and now what we are doing, now since v is a struct of type vertex and we have defined a method on the vertex struct, now we can call the method using this syntax. We can do a dot and then we can call the method name abs. And when we do this, this instance of this struct will be passed to this function, this method, And in this place where we have v, this value will be passed. This instance of the struct where x's value is 3 and y's value is 4. So this is how it works. And if we run the program, we can see 5, because after the calculation, the answer is 5. Now, instead of that, what if we comment this out and we define another function which works pretty much the same as this one, but it does not have a receiver. It is not a method on a type. It is a normal function. And how do you call a normal function? We just pass the struct inside it. And what if we call this? We have the same result, 5. Now, what is the difference? Why did we define a method on a struct? Now, there are a lot of reasons for defining methods. So if you come from a object-oriented language background, then you can relate with the idea of methods with class methods. You have a class and there are methods associated with it. And every time you call a method on an instance of a class, then you have that method limited to that scope. So if you come from an object-oriented background, then it will be a pretty clear idea to you that what is the clear distinction between methods and class methods. Now, using methods, we can assign some behavior to a type so that it is very clear that we have a type and this type has all these behaviors, all these capabilities. It forms one kind of a documentation, and it also has some readability advantage and a lot of other advantages that methods offer. But on a high level, you can simplify it to that level, that it offers some advantages over using normal functions. Now, as I have already mentioned before, that we can use methods on other types also. So we have a type here, type, any name. We are saying my float. This is the name of the type, and it is of type float64. So this is how we can define custom types, user-defined types in Go. We have a custom type here, and we can define methods on this type also. It does not always have to be a struct. We can also define methods on custom types, any user-defined type, any type in Go. Okay, and this is how it works. You define a method, and it takes a receiver, and every time you call an instance of this type, so f is an instance of this type, we are initializing it, and when we call this with ABS, it passes this instance to this receiver and we get the result. So the idea is you can define methods on any type, any concrete type. We'll come to interfaces, but you can define methods on any concrete type in Go. Now, when you are defining methods on a type, the receiver, this part, it can be a value which looks like this, or it can be a pointer which looks like this. It basically has a star in front of the type. Now, what is the difference between the two? If you have a value, then whatever calculation, whatever change you do here, it won't be reflected in that instance of the struct that you call the method on. Okay, every time you call a method, you pass this instance of this struct into the receiver. Okay, that's how methods work. You initialize a struct, and whenever you call this method, this instance gets passed into this receiver. Now, if it's a value receiver, then whatever change you make to this variable, which is of this type struct, this is an instance of this type, it won't reflect in the original instance. But if it is a pointer receiver, then whatever change you make to this struct, will reflect on the original instance. So that is the difference between a value receiver and a pointer receiver. Now, if we run this program, we get 50. Initially, we were getting 3 and 4. By passing 3 and 4, we are getting 5. We got 5 in the previous result. But we used this function scale, this method scale, which actually changes the fields of the structs. And then when we call ABS on it, we got 50 because we scaled it by 10. So this method actually changed the value of these two fields. That is the difference between a value receiver and a pointer receiver. Now, at this point, we can see another advantage of using methods instead of functions? Why do we have methods, and how are they different in behavior when compared to functions? Now we have a function which pretty much works exactly the same as the previous methods. What happens if we remove this star? What happens if we say that v is a value? Now we will get an error here which says cannot use %v value of type pointer vertex as a vertex value. We cannot assign a pointer to a function which is expecting a value. Now in order for this to work, we have to also remove this. Now we are passing the value, but now the behavior also changed. If we run this, we'll get 5 instead of 50. Now to see the differences between methods and functions, we have one method here with a scale method defined on this struct. We have one function here, normal function, which is another method. And here what we are doing, we are initializing a struct of type vertex, and we are calling the method scale, And here, as you notice, it is expecting type pointer, but here we are calling the method on a type value. We did not have to do this. We did not have to do this. V dot scale. We did not have to call the method with a pointer. But in the same way, when we are calling a function, if we remove this, if we pass the value, then Go will throw an error. That cannot use variable of type vertex as a pointer. But in case of a method, Go automatically did the pointer in direction. Go automatically pass the pointer to the method instead of the value. So basically, Go internally did this, converted this into this before calling this method. That's a nice advantage of using method, that you do not explicitly have to think about whether the signature of the receiver matches the instance that I am calling the method on. It can be a value and the receiver can be a pointer, and it can be a pointer, the receiver can be a value. It will do the pointer in direction and it will call with the value. You do not explicitly have to worry about that. Go takes care of it, so that this syntax is pretty readable. Because if you compare, if we had to do this p dot scale, if we had to do this, then it looks very ugly as compared to just p dot scale. So that's why, depending on your use case, depending on the context that it is getting used, Go automatically converts this instance, whether to a pointer, or if it is a pointer, then to a value, using either %p or $p, depending on whatever the signature of the receiver is, so that the program is more readable. That's all it offers. It makes the program more readable by automatically referencing and dereferencing the pointers. Now the question is, when do you use pointer receiver and when do you use value receiver? How do you make that decision? So there are two things that can help you choose whether to go with a pointer receiver or to go with a value receiver. First, if you are mutating any value in that struct instance or to that type, it can be struct, it can be an integer, it can be a float, string, anything. If you are doing any kind of mutation and you want that mutation to reflect on the original instance, if you want the result of the mutation to show everywhere that struct is being used after calling the method, then use the pointer receiver, because using a pointer will actually change the value. Otherwise, if you use a value receiver, it will just create a copy of that and pass it to the method instead of passing the actual variable, instead of passing the actual instance of the struct. Second thing, if it is a very large struct, if it is a huge struct, let's say fields of hundreds and like 50 or 100 fields, in that instance, if you call the same method again and again on that struct, then Go internally has to assign memory locations for all those fields. The fields can be slices, the fields can be other structs, other arrays, integers, floats, complex, any kind of data type. It has 50s and hundreds of fields. In that scenario, every time you call the method, it has to create a copy of that struct and pass it into the method. So that is a little expensive. Now, it is not a huge performance degradation, but it still affects your system in some kind of way. So if you know explicitly that the struct is very large and you want to avoid making copies again and again, then in that case, go with pointer receiver. Otherwise, go with value receiver. So those are two thumb rules that you can use. Now, the last thing to remember is once you make some method, for instance, we have scale method on this. For this, we want to mutate the instance of the struct. That's why you are using pointer receiver. Now, after this, we want to define another method called ABS. Now, ABS returns a new value. It does not mutate the existing instance. But since we already had a method which was pointer receiver, after that point, we cannot, or we can, but we should not use value receiver anymore. We cannot use value receiver anymore once we define a method with a pointer receiver. So the convention is either make all the receivers pointers for all the methods of a particular type, or make all the receivers values. Do not mix. If you mix, very bad things happen because of very subtle bugs that we will see later. But this is something to remember. Once you make one receiver pointer, you have to make all the receivers pointers. Otherwise, bad things happen. Okay, just remember these three rules. If you are mutating, go with pointer receiver. If you want to avoid copying a large struct, go with pointer receiver. Or if you made one method a pointer receiver, always go with pointer receiver for all the methods. Those are the three rules to remember. And those three rules will help you to decide whether to go with pointer receiver or to go with value receiver. Now, in order to understand methods with a real world example, we are again in the FIDER open source repository. Now we have a struct here, whose name is user, and it has different fields. It is most probably coming from a database. Okay, that's why it has ID, name, tenant, email, role, providers, and all these things. And we have different types, and we have JSON tags to parse it properly. Now, the thing to focus here is for this user struct, they are defining, in fact, some methods. And if you take a look at these methods, so this method has provider. What is it doing? It is taking an instance of user whenever you call a user struct, an initialized user struct. With this method, it will pass the instance of that user into this method, and it will have a argument for the provider string. And what it is doing, it is ranging through all the existing providers of a user. So we have an array of providers inside for this user struct. It is ranging through, it is looping through all the providers. And if it has an existing provider with the same name that we are passing here, then it returns true, otherwise it returns false. Now, for this, if you can ask a question that there is no mutation happening here, then why are they using a pointer receiver? Now, there can be multiple reasons, and we won't know it for sure unless we read the whole code base, but we can take some guesses. We can take a guess that maybe tenant struct is very large, or there is another method on this user struct somewhere that mutates the user instance, and because of that they had to use the pointer receiver, and after that point they had to make all the receivers pointer receivers. So as I said, you have to either make all the receivers pointers or values. You cannot mix and match. So the reason can be anything. Okay, and we won't know unless we read the whole code base. So for now, let's just focus on the methods and why are they used and get the feel of it. Why are we declaring methods on this user struct? In the same way, there is a method called isCollaborator, which basically checks whether this user's role is a collaborator role or it's an administrator role. In the same way, administrator is another method, and it checks whether this user's role is a administrator role. Now, by looking at these examples, you can take a fair guess that why methods are important. So if we did not have methods, if we did not have the concept of method, what we would do, we would declare different utility functions. So we can say we declared a function called user has provider, or is user collaborator, okay, or is user administrator. And you can see the pattern here that every time you create a new utility function, you have to explicitly name the function in a way that it is clear that this function is supposed to be used with a instance of the user struct. Okay, otherwise it is very confusing if you just create a utility function with the name has provider, and if someone new in the code base, someone new comes in, then there is no way for them to understand that what is supposed to be the scope of this function, where is this function supposed to be used. And having methods provides this semantic advantage that we have a type user, and a user can have a lot of behaviors. A user can check whether it has an existing provider. A user can check whether it is a collaborator. A user can check whether it is an administrator. And now we don't explicitly have to name the methods is user administrator, or is user collaborator, or is user has provider, etc. Because it is already in the scope of user, and whenever we call it, we will call with user or u dot has provider or u dot is administrator. We have this predefined scope, and it makes things very easy to read. It makes things very easy to process, and the flow of the program is much more simpler. So using methods provides a lot of advantages like this, and as you build more programs with Go, you'll see a lot of advantages along the way. Now we have a very interesting concept called interfaces. And interfaces are something that is very deep into Go's philosophy. And you'll find interfaces everywhere in the standard library, in all the packages. And it's a very important concept to understand. And for now, as long as you understand the basics of it, even if you don't understand completely, it's fine. And we'll use interfaces in our projects, and when we are reading code, we'll look at a lot of interfaces and we'll see how they work. So for now, let's just understand the basics and move on. Let's not spend a lot of time here, because interfaces can be a little tricky to understand in the first look, and you get the feel of it as you work with it more and more. Okay, so let's understand what's happening here. For now, we have a type here, and it is not any other type. It is not a struct or integer or string or anything. It is of type interface. Now, what goes inside the interface type? Inside the interface type, we have methods. We have method signatures. That's all there is to it, to interfaces. We have interfaces, and inside that we have method signatures. Now, how do they work? How are they useful? To understand that, let's dive into the example. Here we are declaring a variable of type interface, of type this appser interface. We have a variable of type appser interface. Then we are declaring another variable of type myFloat. This type is here, and since the order does not matter where you declare the type and where you use it, we can declare the type later after the main function. So we have a type here of myFloat, which is of type float64 internally. This is a user defined type. Okay. Now we are using that type here, and we are initializing it with this predefined function. And if we hover over it, we can find the value of the function. It is some floating point value. Now we are initializing a struct of type vertex. And if we take a look at below, we have a struct called vertex, and this vertex struct has a method assigned to it. Its name is ABS, and it takes a receiver of pointer to vertex, not the value, pointer, and it does some calculations. In the same way, for the myFloat type, which is a float64 type, we have a method which calculates the absolute value and returns it. We have two methods, and for this we are using value receiver. We have a myFloat type, we have a vertex type, which is struct, it is a float64. Now going back to this, what we are doing, we are initializing a vertex type. Now what we are doing, we have a variable a which is of type this interface. Now we don't know what interface does yet. We just know this is of type this interface. Now to this variable, we are trying to assign f, which is of type myFloat, and it works. We don't get an error. Ignore this yellow line. There is some linting error, but we don't get any error here. We can assign the type myFloat to the variable a, which is of type absr. Now, if you remember, initially I told you that since Go is a statically typed language, we cannot assign one variable of one type to another variable of another type. We have to explicitly convert the type. But here we are not converting myFloat into absr, which is of a different type, even though it's an interface type and we don't know what it does, but it is of a different type in Go and it should throw an error, but it is not throwing an error. We can assign f to a. That is the first thing to notice here. Second, we are taking v, which is an instance of type vertex, which is a struct, and we are assigning the pointer of that variable to a, and that also works. We can assign it to this. But now here we see the behavior. When we try to assign v instead of the pointer to v, when we try to assign v itself to a, we get an error. And if we hover over it, it says cannot use v, variable of type vertex, as absr value in assignment. Vertex does not implement absr. Method abs has pointer receiver. Now this is the important part here. Vertex does not implement absr because method abs has pointer receiver. Now we can assign pointer to v to a, but we cannot assign v, which is of type this struct, to a. Why? Because pointer to vertex has a method called abs, but it is a pointer receiver. It is not a value receiver. That's why we can assign a pointer to vertex to a, but we cannot assign a value to a, because only the pointer implements this method. This method is assigned with the pointer receiver, not the value receiver. That's the reason we cannot assign the value to a, which is of type interface. Now, on a high level, what do we understand from this? We understand that an interface type basically provides some kind of behavior that a type should have to implement that interface. This is what interface means. An interface basically gives you a signature, that this is the signature that a type should have to implement that interface, to say that that type satisfies this interface. Unlike other programming languages where we also have abstract classes and we also have interfaces, where in order to use them, we have to explicitly write things like implements, or we have to explicitly use some kind of syntax to say that this type implements this interface. But in Go, the speciality of Go is that as long as there is a type myFloat, and it has a method whose signature and whose receiver matches that of the interface, then we can say that this type implements absr. Since interface has a method whose name is abs, and its return type is float64. In the same way, myFloat has a method. It's a concrete method, and it returns a float64, and it matches this signature. That's why we can assign an instance of myFloat to a variable which is of type this interface. Okay, now myFloat satisfies absr. That's the word to remember. myFloat satisfies an interface as long as it has all the methods that this interface defines. It does not have to do any kind of explicit mapping to the interface. It is implicitly satisfied. So that's a very important concept to understand. A interface in Go is implicitly satisfied by other types as long as they have those methods assigned with them. Now we could not assign the variable v to a because in here the method is assigned with the pointer receiver, and since now v was a value here, we could not assign v to this. That's the basics of interface. We use interfaces to provide some kind of abstract signature beforehand or afterhand. It does not matter. It is an abstract signature that a type can satisfy as long as it has all the methods assigned to them that the interface provides, that the interface asks you to implement. Now here in this example, we have a struct of type T and it has a value which is called S and that is of type string. And we also have an interface type, which is basically a set of rules. We have a set of rules that any type which has a method called M assigned to it will satisfy this interface. That's what it says. Any type which has a method called M assigned to it will satisfy I. It can be assigned to any variable whose type is I. Now, T struct has a method called M and it is doing some basic printing. It has a value receiver. And now here we are declaring a variable of type I, not of type T. We are declaring a variable of type I, and to that variable we can assign a struct of type T. We can assign it a struct of type T to a variable whose type is the interface I, because T implicitly satisfies the interface I because it has a method called M and it satisfies this signature. And now after this we can call the method M using this variable I, which is of this interface type I. Okay. That's how interfaces behave. Now there is some theory to understand here, that what exactly is an interface type, what does it exactly consist of. So you can think of interfaces as some kind of containers, and that's what they are. Interfaces are basically containers which have two properties. One is dynamic type and the second one is dynamic value. Okay. And an interface itself, let's say when you declare a variable where I of type interface I. When you do this, we already know that whenever we declare a variable in this way, Go assigns the zero value of that type. And what is the zero value of an interface type? It is nil. Zero value of an interface type is nil. And when you do this, you can actually call the method I.m here, because an interface has a signature and it has a bunch of methods that you can call on that interface. But in order to call those methods, an interface has to have these two properties inside it. Only after a concrete implementation of that interface is assigned to the variable of that interface, after that only we can call these methods, and after that only it will be valid. Because an interface, when you declare an interface in this syntax, it is an empty container. It is of type nil. It does not have a dynamic type. It does not have a dynamic value. But in this case, when we assigned the type T, we assigned T, which is a struct. When we assigned an instance of the struct to I, when we did this T hello, only after we did this, then we were able to execute this method I.m. And what it did was, after you assign this instance of the struct to the interface, now this container is not empty anymore. It is not nil anymore. Now, this container has two things. One is a dynamic type. That dynamic type is this struct. This struct type is this interface's dynamic type. This is of type T. And its dynamic value is that instance of the struct, which has this field called hello. And now the interface is not empty anymore. Now you can call methods on this interface and it will work as expected. But what happens when you declare an interface and you call it right away without assigning a concrete implementation of that interface? What happens when you call it without assigning a concrete implementation? Now let's test that and confirm our theory. Here I have declared a variable of type I. I is an interface which has a method. Now the program will allow us to call this method M on this interface because it has a signature and it has the method M. But when we call it, when we run this program, we get this error. We get this error which says this, it says nil pointer dereference. We are basically trying to access a memory location which does not exist. It happened because interface at this point interface is empty. It does not have a concrete implementation. Only after we do this, only after we assign a concrete implementation which satisfies that interface, because of the same method signature. Only after we assign it to this variable, then if we call the same program, then we can see hello. What it does, the interfaces behind the scene, it tries to access this type of type T, then it accesses this field and it passes this receiver and it calls this function and we see it in the console. Okay. So basically interfaces are just containers. They provide you with some behavior that you have to satisfy, but they themselves don't have any data. They have to be assigned some data. They have to be assigned a concrete implementation before they are usable. If you call it before that, it will be an error. Your program will panic and it will break. That is something you have to remember. Now, I said before that interfaces are everywhere in Go. And because of the nature of an interface in Go, because of the nature of satisfying behavior, we have a very useful construct which is called an empty interface. This is a type which is called an empty interface literally. Now, what is the property of this type? What is the behavior of this type? When you have a variable or when you have a parameter of this type, you can assign anything to this variable. The Go static type system will not stop you anymore because it is an empty interface. And as we already know that an interface is satisfied as long as you have all the methods that the interface asks you to implement. And since an empty interface has no methods, it has 0 methods, then any value in the Go's type system, any type satisfies this interface. That's the reason we can assign any value to a variable of type empty interface. And that's what we are doing here. We are declaring a variable with type empty interface and we are assigning different values. We are assigning a string here, we are assigning a value here, and it all goes through. It does not stop us. In fact, if you take a look at the signature of printf, it says ... any, which means you can pass any number of arguments. It is a variadic function, which means it can take any number of arguments of type any. Now, any is basically an alias for type interface. So if you take a look at Go code, this is how any is defined. So you have to type any and it has interface. So any is just an alias for interface to make things a little easier to write. Okay. And all the print statements use the empty interface or the alias any to take any number of arguments of any type. It does not matter what the type is, they take anything. That's why they are using empty interface or the alias any. Now, when you use this empty interface construct, when you want to assign any value to a variable, in some cases it might be useful, but when you actually want to use it, since it's empty interface, you don't know what exactly is the value inside it, what exactly is the type inside it. And since Go is a statically typed system, it will not let you use the variable until it knows what type it is. And to confirm the type of a variable, which is of type interface, it can be any interface, we have this feature called type assertion, which is basically a way to cast a value of one type into some kind of interface. It is basically checking whether this type is of this type, whether this interface is of this type. Okay. So let's just look at this example to understand this better. What's happening here? We are declaring a variable which is of type empty interface, which means we can assign any value to it. It can be string, boolean, number, anything. And here we are assigning a string here to this variable. At this point, what we are checking, this syntax, I dot and a type name. This syntax is basically saying whether this variable I is of type string, whether this variable I is of type string. If it is of type string, until here it says interface, but after the type assertion, we have the type string here. And if you print it, you will get the result. And in order to check, in order to provide some kind of assurance that this type assertion was successful or it was failure, or this variable does not satisfy this type, in order to provide that mechanism, this type assertion provides two values. The first is the new variable, which has the type this, the type that we are trying to assert to, and a second variable, which is a boolean, which says whether the type assertion was successful or not. Okay. And using this, you can check the value and the success or failure. What happens if you use a type assertion? What we are doing here, we have a variable which has a type empty interface, which means any value can be assigned to it. And we have assigned a value string to it. And we are trying to convert a string type to a float type. And we are asserting this type. We are saying if this variable is of type float64. We are also doing it here, but here we are doing it without this boolean. Now, if you do it like this, the program does not break. The program does not panic. It does not error out. We have an OK, which is false, because a string value cannot be converted into a float value in any way. But in this case, we are not taking the boolean. So the behavior in this case is the program panics. If you're not taking a boolean in the second value of return type, then this program will error out. And if we try to run this, it is not a compile time error, it is a runtime error. Then we see the results here up to this point, but when we execute the last statement, we get a panic because we tried a types assertion without taking the variable OK, without taking the result of the variable, whether the result was success or it was a failure. Now, to assert to this type again and again is a little cumbersome. That's why Go provides a very nice construct for us to systematically check a list of types that we want to satisfy to. And if it matches one type, then we can perform whatever operations that we want to perform on that type. So for that, we have this example. Here, what we're doing, we have a switch statement. And in this switch statement, we already know that in the initial part of a switch statement, we can call an expression. So it is calling this expression and it is doing a type assertion. So this is basically a type switch. This is something you'll find a lot whenever empty interface is used. And this is a type switch. What it is doing, it is tying a assertion here at this statement, and this type, the actual type of this variable, this I, will be assigned to V. And then we are checking different cases. We are saying, find out the type, the dynamic type of this variable I, and check whether it is an integer or not. If it is an integer, then come to this and break out of this switch statement. If this is a string, then come to this and break out of this switch statement. If it does not match any of these cases, then come to this and execute this default statement and break out of the switch statement. And then what we are doing, we are trying this example where we pass a integer first, then a string, then a boolean. So if we run this, we get different results. For the first one, we are doing some integer calculations. Since the type here satisfies integer, we can do mathematical calculations here. Until this point, we cannot do anything with I. We cannot do anything into I. Let's try to do something here. Up to this point, we don't know the exact type of I. So if you do this, I equals to I plus 2. If you do this and if you hover over it, it will say invalid operation I plus 2 mismatch type interface and integer. Basically saying you're trying an integer operation on a type which is of type empty interface. You cannot do that. Okay. And in the same way, if you try to call length on I, if you hover over it, it will say invalid argument variable of type interface for built-in type length. You cannot call length on this type interface. Basically, you cannot do anything with this type unless you cast it explicitly to some type, some basic data type or to some complex data type, anything. You have to explicitly cast it to some type. Since Go is a statically typed language, you can use this construct. You can use this empty interface to pass a value of any type. But when you want to use this, when you want to use that value, you have to explicitly assert it to some type. It can be integer, string, boolean, or anything. And a type switch is a very nice way to conditionally check different types and to perform different operations depending on the type of this value. And as you can see that in the first function call, it was an integer, that's why it landed here. In the second one, it is a string, that's why it landed here. And in the third one, it is a boolean, that's why it landed in the default case, because we were not handling boolean. Okay. And now since we know about interfaces and we know about type switches and different types of dynamic types, there is a concept that is used heavily across the standard library of this interface type, which is called stringer. Now there are two things to notice here. First, in the standard library or in different places where people are using interfaces, you will see this pattern that all the interfaces are ending with this suffix er. It's a stringer or a printer or a downloader or something, a er suffix, because of the behavior. Because interfaces define a set of behaviors, this er thing, this er suffix conveys that emotion more explicitly. So this is one thing to notice here. Second is, a stringer interface is defined in the standard library. So this is what it looks like. Let's clear this. We have a type in the standard library which looks like this, type stringer, and it's an interface. It starts here, and inside that there is one method which is called a string method. Okay, and this is an interface which is defined in the standard library, and it is used heavily everywhere. Basically, a type, it can be any type. It can be a struct, or it can be a user defined type of type integer, float, string, anything, a map, anything. Now that type is called to be a stringer. It's called to be implementing stringer as long as that type has a method called dot, as long as it has a method called string. Now it is important because in the previous example we saw that using a type switch we can check that whether a variable satisfies an interface or not. Okay, we can check that. So in functions like this, in functions like sprintf and println, if you take a look at this, they take variadic arguments of type any, which is an alias for type interface, empty interface. Now they demand that whatever you pass, they can be any value. That's the reason they have said any, which is an empty interface. They can be any value, but they have to satisfy the interface stringer, which means they have to have a method which is called string. So in this example, we have a struct. And it has a method. What this method is doing, it is taking the instance of the struct and it is printing the name and the age using %v. Basically, it has a string method which represents this struct in a string format. That is the reason we can take this instance of the struct and we can pass it to println, because now this struct satisfies the interface stringer, which this println, printf, sprintf functions require. They require your type to implement the stringer interface, which means your type has to have a method called string. Now what happens if we comment this out? What if we run this? Now if you run this, they use its internal representation. Since this type does not implement stringer interface anymore, they have some default representation of how a struct should look like, and that's how they're printing it. Okay, they don't follow this format anymore. But if you uncomment this and if you run this again, now if you see, this format matches this method, because when you pass any type to println, what they do, they check whether this type implements stringer interface, which means whether this type has a method called string. If it does, then they call that type's string method. If it does not have a string method, that's when we commented it out. It will use the default representation of the any struct that Go has internally. Okay, so that is another thing to keep in mind. Now we have another interface, a very famous interface, which is called error. And you will see this everywhere in Go. This statement, if error is not nil, do something. If error is not nil, do something. Since Go follows this principle of explicit error handling, it follows the principle of explicit error returning errors as values and all these principles related to errors. Go has an interface called error. It has an interface called error. And it is an interface. And since we know the zero value of an interface is nil, that's the reason we can check that whether it is an empty interface or if there is an error in that, or if there is a concrete representation of some type which satisfies error and it is present in that. Okay. And let's look at this example to make this more clear. Now, here we have a type struct which has two fields, when and what. When is of time.time. There is a package called time and it is of type time of Go of time. There is another field called what. It is of type string. Now, this struct has a method associated with it called error. It's called error. And it takes a pointer receiver and it prints the when and the what with using fmt.sprintf. By the way, sprintf basically, it does not print the formatted string into the console. Instead, it formats the string and it returns it if you want to return it. It basically constructs a new string. It does not print it or anything. That's why you're using sprintf. That's what this error method is doing. Then we have this function run and it basically returning an instance of this struct with these two values, time.now, which basically takes the current time, and string call it did not work. And in the main function, we are executing this function, and if it returns an error in the signature, we are saying this function returns an error. We are executing this function and we are saying in the signature that it might return an error. That's why. And it returns this error type. And there are some things to notice here. First, we are declaring a custom type, which is called myError. But when we are returning from this error, it is not a myError type. We are returning a generic interface called error. Now, error is another interface like stringer, which is defined in the standard library of Go, which is provided by Go. And it looks something like this. It looks like this. Type error and it starts. And inside that, it has a method called error. As long as any type in Go, it does not matter it's a struct, integer, float, string, map, does not matter what type it is. As long as that type has a method called error, like we have here, it is of type this interface. It satisfies this interface error. So we can use that type in place of this type. That's what basically interfaces do. As long as you satisfy the signature of an interface, you satisfy the requirements of an interface, you can use your type in place of that type, in place of that interface type. So having that in our mind, this function, this run function, it says in the signature that it is returning a type of error, which is an interface, but it is returning a concrete type. It is returning a type struct, but that struct has a method called error. And it is doing some kind of formatting, string formatting. And now the reason we are returning an interface instead of saying in the signature, instead of saying the return type is of type myError, the reason we are returning an interface is because of this. When the caller, the function that is calling this one, the main function, it calls run. When it calls it, it checks whether the value of error is nil or not. And since we know that an empty interface has the value nil. Since we have this knowledge, since this is a fact, what now we can do is every time we run a function, if that function returns an error, then we can check if the error is nil or not. Since it is an interface, if it is not returning an error, if it is returning nil, then this case will be false and we will proceed in the success flow. And if it is returning some value, it does not matter what value, it has to satisfy the error interface, and it returns some value, some concrete implementation, then the error is not nil. In that case, we will succeed with the error flow. Those are two reasons we use error interfaces everywhere in our program. That's all about interfaces that we need to know as a basics to start out writing more programs. Now, there are a lot of different behaviors to interfaces, and there are a lot of concepts associated with interfaces that we will explore as we learn more, as we read more code, as we write more code. But as of now, that's pretty much all you need to know. Now let's take a look at some examples of how people use interfaces in real world apps. Now going back to our example, we can see there are interfaces everywhere. People are using interfaces to define behaviors, to define methods, get email, get name, get user, get kind. Interfaces are used to define behaviors everywhere in the code base. Now there are a lot of different use cases associated with it. One particular use case that interfaces have in a real world app, in a backend app, is when you are writing test cases. As we know that in backend systems, we have different layers of system. We have, let's say in the base layer, we have repositories. Repositories. Above that, we have services, and above that, we have controllers. Repository layer basically deals with all the database operations, all the database queries and inserts, removing all these core database operations. And the service layer uses this repository layer to mix and match different business logic with different repository methods. So it can execute some repository method like create an entry in database. Then in this service layer, it can send an email, it can send a notification, and it can schedule a task. All these things are responsibility of service layer. It basically orchestrates different repository methods with business layer. And then there is the controller layer, which deals with HTTP related stuff. Like it receives the body, it receives the query parameters and all, it parses it, it validates it, and it passes on all those input arguments to the service layer, and whatever things that are returned from the service layer is passed on to the controller layer, and it sends those responses appropriately with appropriate HTTP status codes and appropriate data format, and etc. Thus the overall flow looks like in a typical backend layer. Now some backend system might not have a service layer, the controller might use the repository layer, but it's just all about terminologies. Typically we have 3 layers. Now we have this repository. This is an open source repository called Incubator Answer, and you can take a look at it. This has very good patterns that you can learn from, and scalable patterns, scalable backend patterns that I personally use to learn a lot of stuff. So anyway, we can see here that there is an interface here. We have an auth service, basically a service which don't need to understand any of the code, just focus on what I am explaining here. Okay, we have an auth service which basically deals with different operations related to authentication. Okay, we have an auth service. It's a service layer. Above that there is a controller layer. Below that there is a repository layer. Now this auth service in argument in its parameter, to initialize this auth service, Go has a very good dependency injection convention. We will explore more about dependency injections and all in later videos when we are building projects, when we are reading different project codes. Now, what dependency injection basically means, instead of directly importing the auth repo, you take the auth repo implementation as a parameter, and then you return this instance of auth service which has all these methods. So this is a struct. A struct has different methods associated with it. If you scroll down, this is all these methods in this user service struct. Okay, we have explored methods just a while back, so you should have some idea that what's happening here. And what's happening, it is taking an implementation of auth repo, the repository layer for authentication, and it is returning a service, auth service, with auth repo inside it. Okay, that's what's happening here. This is a constructor, you can say the initializer of this auth service struct. Now here auth repo is not a concrete implementation. It is not coming from a struct. This auth repo is actually an interface that is declared in the service layer itself. There is one convention when you are dealing with interfaces, when you are declaring and using interfaces, which are always, interfaces should always be on the consumer side. Now, of course, there are exceptions to it. very valid exceptions, not very rare also. But it's a general thumb rule, a very generic thumb rule that works most of the times, that an interface should always be on the consumer side. What do we mean by consumer? Whoever is using that interface, they should declare the interface, and the producer should satisfy that interface instead of the other way around. The producer should not define an interface and export it. The consumer should define the interface and the producer should satisfy the interface. Now, auth service takes an interface instead of a concrete implementation, instead of a concrete struct. Because the reason is, in a typical backend system, you have all these services, repository, methods and all, a lot of functionality. Now, every time you change something, you have to test all the previous functionality, that all the previous functionality is intact or not, whether you broke something or not. And in order to do that, we have tests, and we write tests to verify if all the previous functionality, all the present functionality is intact or not. Now, during testing, what happens? You have a local database. You have a local database, and you have a production database. You have a database for tests. Now, if auth service took a concrete implementation instead of an interface, it is very difficult to replicate all these, to test all these methods during tests. So there are different types of tests. There are unit tests. We have not gotten into tests yet, but on a high level, there are unit tests, there are integration tests, and there are end-to-end tests, end-to-end tests. During unit testing, when you are unit testing services, when you are unit testing your business layer, you don't actually want to make database calls. Let's say you want to make your tests faster. You don't want to spin up a Docker container, and you don't want to do all those database queries and all those inserts operations. You don't want to test with a real database. What you can do, since we are taking an interface instead of a concrete implementation, instead of a concrete struct, what can happen in this case? When we are unit testing our services, the caller, the test which is testing this auth service, it can pass a mock. It can pass a mock struct. A mock struct, let's say it is called test auth repo. And this struct has all these methods, all these same methods. And that is the reason it can pass that struct to this auth service, because this auth service takes an interface. And as long as the struct that is getting passed as a argument, it satisfies that interface, we can pass it. The Go compiler will not throw an error. And so during testing, what happens? We create a mock repo instead of the actual auth repo, which calls all these database methods, which makes all these queries and inserts and operations, deletes and all. We create a mock repo. What it does, it, instead of doing database calls, it just returns strings. It returns hard-coded strings, or it does some very simple calculation, and it returns in-memory structs or in-memory slices instead of doing actual database operations. Now, what is the advantage do we have? During our actual production deployment, what we can do in our main code flow, not our test code flow, in our main code flow, we can pass the actual repo, which has all the database related methods, which has the concrete implementation of database related methods. Now, during our CI/CD pipelines, when we are calling our tests, there what we can do, in another code flow, we can pass the mock. Now, both this actual database repo and this mock repo, both of them implement this interface. Both of them implement this interface. That's why we can pass both of them to auth service. Now, auth service does not care whether it is a concrete struct or not. It just cares about that it satisfies this interface as long as it has these methods and it has these parameters and it has this return values. It will call the auth repo like this, and depending on what is the actual implementation, whether we are in the main code flow or whether we are in the test code flow, depending on that, whether we'll get a hard-coded value during tests and we'll get actual database value during our main code flow, during our actual production environment. Now, that is a huge advantage. If you are someone who has written tests before, this reduces a lot of boilerplate code, it makes the program flow much cleaner, since we don't have to use any external testing libraries or packages to create mocks and all. Go natively supports all those mocking and all because of the interface design pattern. Okay, now that is just one of the use case out of hundreds of use cases that interfaces do. We already saw different cases, like we have stringer. Because of stringer, we can pass anything to printf, and as long as that type, it can be struct, integer, or string, or boolean, anything, as long as that type has the method string, we can pass it to printf or sprintf or any of the print function. Same way, as long as any type that has the method error, it satisfies the error interface, and we can treat it as an error. In the same way, there are a lot of interfaces in the standard library. We have io.reader, we have os.file, a lot of interfaces. Because of this interface's implicit satisfying nature, there is a lot of composition that we can achieve using the interface pattern. And we'll explore that more when we are going through different resources, when we are reading more open source codes, and when we are building our own projects. That's all about interfaces for now.